Okay, hi everyone. Thanks for being here. Thanks, Livia, for the invitation and a very nice introduction. So I'm going to talk about tracing the assembly of the very first massive galaxies using a digital twin, which later you will know what I mean by a digital twin. This presentation is based on like two papers that we published in 2023 and one very recently. And the topic starts with JWST pushing the frontier of redshift, basically. So here I'm showing a plot by Takela et al. 2025, where they show the redshifts that we have got from galaxies at redshift larger than 10. So basically with the spectroscopy, mostly. This one doesn't work. Oh, yeah. So the colored galaxies are spectroscopic redshifts for galaxies that are redshift larger than 9 and 10. And then these guys are the photometric ones. So basically, it's amazing that like after in a few years, we have got almost more than 40 galaxies spectroscopically confirmed at redshift larger than 10. And amazingly, for some few months, we had this guy, which was the JWST 14.0 as the highest redshift candidate at redshift 14.17. So there is a very nice spectrum from the nearest spec. This galaxy here that you're seeing, and the other guy is the background. And this guy was the highest redshift galaxy for some months, but then the galaxies still are there, and we are finding even further galaxies. This is the MOM-Z14 galaxy at redshift 14.44. So now this is the record holder for the furthest galaxy at this in our universe that is being found with the James Webb. So basically, one of the biggest problems that has opened up since the beginning of the works with the JWST is that if we look at the like mostly here is the UV luminosity function for these massive galaxies. For instance, look at these green points. They are basically, all the models are underestimating these guys. So none of the models, for instance, here you are showing different simulations. There are some analytical works of the semi-analytical analytical works for the galaxy formation. So basically, we are finding these UV bright galaxies with a large number that we were not expecting with the lambda CDM model that we had, like the standard lambda CDM model. So in this past few years, there have been a lot of effort in finding a solution. Why these are not? Why we have like this many massive and let's say luminous or massive galaxies at this high redshift? So there are different type of efforts. Like within, you can choose your favorite one, either staying within lambda CDM or going beyond. So staying within the lambda CDM, there are different works, like for instance, increasing star formation efficiency works that they are trying to, for instance, a feedback-free model by Deckel, or trying to explain this with the scatter between the UV and the halos that you have like in your standard lambda CDM halos. And there are like stochastic star formations that if you consider, you can a little bit like the curves that I was showing you before, you can kind of solve for that. Or you can go for other physical models, for instance, for the ISM, for the dust, assuming you have less dust attenuation in your galaxies, or contribution from AGN. And like there are different kind of works that you can do within the lambda CDM that you can kind of account for this excess of the UV luminosity. Since the models that I was showing before, they are mostly based on the semi-analytical model or the simulations that have not like, they don't have like the detail of the ISM that we need to explain them. Or you can go like on the beyond the CDM models. And there are also a group of works that are working on this. For instance, they are modifying the primordial spectrum, power spectrum of the universe in the beginning of the formation. Or you can change the dark matter in your models. So you can try different ones like axions and all different things. Or you can consider early dark energy models And for instance, here in this model, they show that changing this lambda, omega lambda, you can have different luminosity functions for these bright galaxies. So basically, you can explain this number density that we are finding. But like as someone who is working mostly with the simulations and like more excited on the individual galaxies rather than their group behavior, I'm more interested in the internal properties of these galaxies and to understand what we can learn from these very first observations at high redshift. And even from the observational side, there were a lot of efforts from the first cycle. It was a bit problematic in the beginning, especially when there was only photometric data. For instance, here I'm showing the CD that they got for a galaxy which is called the GHZ2 at redshift. It was thought it was around the redshift 12, and with the stellar mass of around 10 to the 8, and the star formation right after 20. These kind of photometric data were difficult to go beyond because, like, these kind of high redshift galaxies, they could either be even at a lower redshift, so there are like the probability distribution of the SED fitting that they could even be like a dusty star forming galaxy at redshift 4 or at redshift 14 or 12, similar to this guy. So what people did was to search the emission lines with another instrument like ALMA. For instance, they tried to go for O3 emission lines. So this is one of the first efforts that people did for this GHZ2. But then there was no clear detection because we didn't have exact redshift range for this when it was a photometry. So there was no detection, unfortunately, back then. But then there were like different kind of solutions why this is happening. So basically, as I said before, this could be due to the lower Z interlopers. For instance, it could be a dusty star forming galaxy at redshift 4. This is one example which happened to be at lower redshift. It was supposed to be at redshift 16 and the highest redshift galaxy, but ended up to be around redshift 4, which this small probability was there. So this was one of the reasons. But then another reason is that these kind of follow-ups with ALMA were using the DDT programs. So basically, they are too faint, these galaxies, to be detected with the DDT. So there was a lot of discussion around this. And us as simulators, we were like wondering what's happening in these very high redshift galaxies that, like, if we see them with JWST and then we are following up them with ALMA, we are not seeing anything. So we have this set of simulations in Pisa, which is called SERRA, and they are basically we are following up star-forming galaxies in this redshift range with the stellar masses from 10 to the 6 to few 10 to the 10 solar masses in stars. And you can see here I'm showing different zooms of this one of the galaxies. So you can go either from the, let's call it cosmological scales down to interstellar medium scales, which we are seeing it here. So basically, our question was, if we go and in these simulations look at the galaxies around redshift 11 to up to 14, which basically is similar to the guy, for instance, in GHZ2, how many galaxies we find and what are their properties, basically. So we found 366 galaxies in this redshift range, but only 42 of them was sitting in the stellar mass and star formation range of the JWST detected galaxies. But then our idea was to understand their far infrared properties, to understand like the O3 emission in particular. So we modeled their O3 emission line, basically using like some post-processing. So here I'm showing these all the 300 galaxies that I was talking about on the LO3 over SFR plot. So you can see this colored one are the galaxies, which I showed you. There are like 42 of them, which they sit in the star formation, redshift, and stellar mass of these massive galaxies at a high redshift. But what you can see is that we found a very broad range for the O3 emission line, O3 luminosity. And already from this plot, you can see that these are color-coded with the ionization parameter, which are showing that how many ionizing photons have been escaped from this the ISM of this galaxy. So basically, the higher this U ion, the higher your O3 luminosity. So we found this range. But like you can see also, this is these are two prediction, like from the redshift 0 estimates. So we found that already in this sample, we have few galaxies, like 3, 4, that fall along the line of the metal poor galaxies. So, and the estimates were basically around the upper limit, for instance, for this JWST guy. So already from here, we were expecting to detect this galaxy. And then we wrote this paper explaining why we are not like the ALMA non-detection of these JWST galaxies. However, I was basically very like skeptical writing this last sentence in this abstract. And we said that if this guy, which is called Amaryllis, later we will know about it more, if we were lucky enough that these high redshift observed galaxies were similar to this GH our Amaryllis guy, and it had the perfect situation. It has a face-on view that the previous of maximum is short enough, that like your line flux is high enough that you can detect this. You need 2.8 hours on ALMA, on source with ALMA to detect these guys. And this was back in 2023. So in the meantime, this paper got completely forgotten until the JWST, the highest redshift galaxy, came in, and everyone was excited about it. So from both two groups, people put on like DDT programs, since they knew the redshift of this guy with near spec. So they went with ALMA to detect O3 emission line. And really super luck. So they detected O3 emission line in this galaxy 2.8 hours on source. So this is kind of like one of the most exciting time of my career, I would say. When I saw the number, I was like, this is unreal. So basically, but this was for the higher redshift galaxy, redshift 14. And since then, people are trying, since there is a near spec observations, we know the redshift of most of the galaxies, so they can go with ALMA if they are in the correct location. However, so far, for these massive early galaxies, there have been only two galaxies that we have ALMA and JWST synergies. So one guy is this GSZ14. So for which there is like now the near spec data, so they have perfect like the redshift we know, the stellar mass, I wouldn't say perfect, but we know it, it's around 10 to the 8. The star formation rate is around 19. And they have O3 emission, but also C2, they went for C2 emission, but they didn't detect anything, they put on an upper limit. So they find these very high over O3 over C2 line ratios for this galaxy. And this is GHZ2 that I showed you already, where there was no ALMA detection in the first place. But after they got the JWST, the near spec redshift, with more integration time, they got also O3 emission for this. So basically, for these two galaxies, we can better understand the ISM of these structures. So with that, I will bring you to this digital twin that I talked about. So after these observations were in, we were like, why not looking at Amaryllis in more detail, since we had the prediction only for one redshift in that plot that I showed you. It was only an integrated property. And I would like to introduce this new term that we kind of introduced in this paper, which is kind of borrowed from earth sciences. And it's basically a simulation that is not only producing the integrated property of galaxy, but then it can resemble their internal properties, dynamics. So going a bit more detail on the property of the galaxy rather than only producing, for instance, the stellar mass, star formation rate, or total O3 luminosity or any emission luminosity. So this is basically the evolution of this galaxy, the main halo of the Amaryllis I'm showing. Here's the star formation, stellar mass as a function of time. So basically, we are following this galaxy from redshift 16 to redshift around 6, so 7 point something, 6 point something. And here, these lines that you can see, these are like other merging companions that on the way they join this galaxy, and then they make the galaxy up to redshift 7. And these data points are basically observations, the redshift larger than 10 observations that I was showing you. So it's quite strikingly is producing the stellar masses of this very massive galaxy of high redshift. And this is a kind of rare system in zoom-in simulations. It's not like in SERRA we've got one, and so far I haven't seen any other paper. They are claiming that it's because it's very difficult to have these massive galaxies when you have a zoom simulation because of the area that you are simulating, basically. What is nice about this plot is also I would follow you to lower redshift. This kind of shows these guys are the massive reionization era galaxies. For instance, the Rebels Rebels sample here I'm showing. Okay. So basically, it's kind of connecting the very massive early galaxies like JWST 14 to the most massive galaxies we have found so far in the universe in the cosmic reionization, which is the Rebels 25, which is this guy. So maybe these very redshift, high redshift galaxies are basically progenitors of the EOR galaxies. And we can go in detail during the evolution of this galaxy, look at the star formation. Basically, star formation history of this galaxy is very bursty, and these are mostly with the merger-driven burst. So here you can see the lines are showing different major mergers that are happening in this galaxy. And after any merger, you have this peak of star formation. So you produce this kind of bursty star formation histories. And here you can see a nice plot from different evolution of this galaxy. So here is at redshift 14, so this little guy here. And then down to redshift 7, when it produces this kind of rotation-dominated structure. Already from the maps, you can, from the images, you can appreciate that. But we talked about the far infrared emission lines that in these very high redshift galaxies, they are basically very high O3 over C2 emission line that I showed you. We looked at the evolution of these parameters, for instance, the O3 over C2 along the redshift. And we find that this also is very bursty, I would call it. And there are these kind of extreme far infrared emission lines that are happening during the evolution of this Amaryllis. And this happens mostly when you are after a merger. So basically, your mergers are producing this kind of starburst, and these starbursts are producing this high U ion, and this high U ion, which is like the ionization parameter, is producing the high O3 over C2. And but these are very short-lived merger-driven starburst, which are you can appreciate it here basically. And these kind of parameters that we got for the for Amaryllis are along the simple 1D models that people do with, for instance, for JWST 14 in terms of the density, in terms of the ionization parameter. But we are getting lower metallicities than what is what they get from the, because they expect to have higher metallicities to produce this kind of emission lines, while we claim that this is not really needed, because when you're assuming your galaxy is in a hydrostatic equilibrium, that then you're using the emission line modelings, for instance, with cloudy, you need these higher metallicities. While if you do it like in a special resolve in your simulations, you basically don't need very high metallicities to get this high ionization, high O3 over C2. And this kind of merger-driven bursts, actually, they also, we can go deeper, try to have some predictions for follow-up observations. If we go and observe these galaxies even deeper with ALMA or other instruments, we find that this kind of high over O3 over C2 are happening when you have this kind of broad emission lines, I would call, in your O3 emission line. So this is kind of showing it might be that these are like outflows outflows that are produced during this post-merger phase. But I would, as a kinematics, I don't find the adjective idea. I wouldn't like go further with this kind of modeling in terms of the broad emission lines, because already at this very high redshift, disks are in place. So rotation is in place. And having rotation at this very high redshift means that you have this kind of complexity in your kinematics modeling that only fitting your Gaussians, fitting your profile with two Gaussians is really as oversimplification. And rotation, especially if you don't have like the inclination correct, then you can mess up with the quantities, for instance, in terms of outflow rates, all these properties. For instance, here I'm showing narrow and broad with different velocities, but this can be very complicated. So we have to care about this even at a redshift larger than 10. And this is not just from the simulation side, actually. Oh, no, I forgot. I will go first this and then that one. This is not happening only in the simulation side, but also in the observation. Actually, they are trying to kind of see this kind of rotation. For instance, this is for a galaxy, the JWST 14, where they see it. There is like a tentative rotation at redshift 14. And here they claim that if we get the higher resolution ALMA, we should be able actually to detect properly the rotation at this high redshift. But personally, I would say that for this kind of science, we need the upgrades for ALMA. So for instance, ALMA 2040 can be really transformative in this field. And as a last thing, I would say that this kind of situation is not, this kind of like halos are not happening in, we don't need to change our cosmology so far. So at least one galaxy is like, in the observation, we find 2 galaxies. In the simulations as well, we are doing as observers. So these kind of systems can be reproduced within lambda CDM. We don't really need a different dark matter even or any other kind of changes. The only thing that here I'm showing is the dark matter profile of Amaryllis. And we find that lambda CDM was okay, only that what you need for this kind of situation is that you have a chord profile. So basically, this is kind of a Burckhardt profile to have your disk of the galaxy to form already at very high redshift. And then the galaxy, the mass of the galaxy is like already there that we can reproduce the JWST 14 or any massive galaxy that we are seeing so far. So I would leave you with my conclusion. So basically, this JWST and ALMA observations are basically unveiling this kind of rare system that we were not expecting, rare bright system that we were not expecting to be that many at high redshift, which are kind of challenging star formation, galaxy formation models. And there are different efforts to solve this, and they are all going in a direction that I think maybe in a decade, we are going to have a different kind of galaxy formation model than we have right now. And then these kind of digital twins also are, in my opinion, interesting to look for, even though they are just 1 or 2 or 3. But we can go deeper and have predictions for like the observations that we have and to understand the observations that we have. So I will leave. Thank you.
Thank you very much. So there is time for questions. Marco.
Something very basic. Can
Yes.
you tell us in a few words what kind of simulation is this?
Yes.
What's the resolution?
Yeah. So these are zoom-in simulations. Basically, we have the resolution that we go down to 10-ish parsec. The stellar mass of the galaxies we are interested in are basically star-forming galaxies or Lyman break galaxies around EOR galaxies, EOR time. And then there is the radiative transfer on the fly for these simulations, as well as the chemical network to produce the H2 molecule, which is important for this post-processing that we are doing. And also it's important to reproduce the cold gas structure of these systems that then you can reproduce the disks and all these details. So if in,
What code?
it's Ramses. Oh, the code you didn't ask. Yeah. Yeah. It's Ramses space. It's Ramses RT.
Carlo.
So did you measure the evolution of dark matter profiles from hydration to redshift 7?
Not yet.
Just to have an idea.
Not yet. Yeah, that didn't go into the paper, but yeah.
Thanks. Going back to your introduction, you could explain the luminous function.
No.
No,
I wouldn't go with
yes,
the.
but I mean, you listed a series of
Yeah.
points. So probably the main reason in order to, I mean, to reproduce the luminous function could be the star formation history that is up and down.
That's also one of the things that people are showing with the stochastic star formation rate, but there is a debate. So some simulations show that stochasticity is enough to reproduce this UV excess, but some not. So there is not yet, for instance, from SERRA side, that the stochasticity is not enough to reproduce the UV luminosity function. Yeah. And the UV luminosity function at redshift 14 is really unconstrained. There is just 1 point, so it's very, very hard. So the point that they have is from 1 point, 1 galaxy.
Questions? Franco.
Again, just to connect to your initial proposed solutions, like the one within lambda CDM, the one beyond lambda CDM. So what you showed us is that, so what's the solution? So you're working within lambda CDM.
Yes.
And
For
fact,
single galaxies like that you have, so because like going from the detection of from observations of one UV luminous galaxy to a luminosity function, there is like a lot considerations in between. I'm just saying that with lambda CDM physics, and then doing assumptions mostly on the ISM side and trying to reproduce the galaxy, you can do it without lambda CDM. But if you want to reproduce the luminosity function that they are finding, that's another thing. So for that, also with the zoom-in simulation, I wouldn't go that way. So you need to have also multiple regions of the universe, and also so then I didn't mention here. I just said the good is like nice stuff. This is not so in terms of the UV properties. Actually, the SERRA galaxies are very dusty. So actually, if we want to also go for to reproduce the UV properties, we need to change our, for instance, feedback models inside. So with that feedback model can be, for instance, adding, I don't know, like pre-supernova feedback that can wipe up your galaxy from dust, and it can be very bright in UV, while or other adding AGN, which we don't have AGNs in this massive, even in this massive halos. So there is a lot to do, even within lambda CDM, I would say. Even though, I mean, I like the theoretical works that are being done beyond lambda CDM, but it's a bit difficult to constrain them.
you have a question on that.
Yes, there is a question online. I'm gonna read it. Sorry if I missed this point. How long does it take to make a digital twin? And is it possible for several galaxies or one galaxy at a time?
It's a very difficult question. It's like, it depends really on your resources. So for the total SERRA galaxies that we had, like, if I'm not wrong, half of it was run on Chineka, and it was around 200 million CPU hour. So it really depends. Then it depends also the type of the code that we have, and what kind of parallelization we can do. So it really depends.
And then there is the post. If I may add, there is the post processing, so of the ISM.
Yeah, exactly.
Part.
Complexity on top, exactly.
Thank you. Okay.
Thank you.
Thanks you. Okay, so I think we are running out of time. Let me see if there are any other questions online. No. Any other question here? If not, let's thank Mahsa again. Thank you so much.